In this lesson, we will talk about how depth of field works and how aperture affects depth of field. The concept of depth of field is based on the human eye's ability to detect an area that is no longer sharp or in focus in an image. Two sets of eyes may perceive sharpness differently, but the photographic community has decided on a standard for acceptable sharpness. This is called the circle of confusion, and yes, it has a terrible name. The circle of confusion is based on the smallest perceivable detail we can see in an 8 by 10 inch image at a viewing distance of 25 centimeters. The standard is based on a more average level of vision, and folks with 20/20 vision can actually see details 1/3 the size. This means that what appears to be sharp for one person will not appear sharp for someone with Superman vision. If we were to take the 8 by 10 image and enlarge it at the same viewing distance, we would see more detail in the image. Now, things that looked sharp compared to the point of focus may not look sharp, and the depth of field would have been reduced. Similarly, if we shrink the image down, we will see less detail in the image. Compared to the point of focus, a lot more of the image looks to be sharp. It works like this. A person with good vision is said to be able to see details as small as 5 line pairs per millimeter, which is the equivalent circle of confusion of 0.2 millimeters in the final image. If this is the smallest detail we can see in an 8 by 10 print, how does that translate to what's happening on the sensor? To figure this out, we need to find out how much the print has been enlarged from the sensor size. If we shot with a full-frame camera, this is about 7 times. We take the long side of the 8 by 10 image and we convert this to millimeters. We take 254 millimeters and we divide by the long dimension on a full-frame sensor, which is 36 millimeters, and we get 7. The 8 by 10 has been enlarged 7 times from the image captured on the full-frame sensor. Now we take the smallest detail, or circle of confusion, that we can see in the 8 by 10 image, which is 0.2 millimeters, and divide by 7. And we get 0.028571 blah blah blah. But this is usually rounded to 0.029 or 0.3 millimeters. This means that on the sensor, points in the scene that create a blur spot larger than 0.03 millimeters will, to most people with good vision, look unsharp. Those points are outside the depth of field. Let's look at an example. In this illustration, I have placed a series of circles in a line and offset them so that they extend away from the camera in the Z dimension. In a moment, we will look at these circles through the eyes of this camera represented by this pink line. The line shows the viewing angle of the lens and also where the plane of focus is. Just like in real life, there's only one precise point at which this scene is perfectly in focus, and everything else in front of and behind that point will be getting less sharp. As you can see from the camera's perspective, we can see that some circles are definitely not sharp, and there are some that are. The point where they go from unsharp to sharp is not 100% clear. You really have to look. To my eye, I would say that these group of circles are sharp, and the ones to the right and to the left of this group are unsharp. This is very similar to how the circle of confusion works. We know that only one of these circles is perfectly in focus, but because of the size of the enlargement, it looks like several are acceptably sharp. This area is our depth of field. Let's look at another example. In this example, we are looking at an exaggerated illustration of how different points are focused on your camera's image sensor. In real life, these points would be microscopic. This point is where our scene is in focus, and we would call this the focus plane. All objects on this plane are in focus. Just like in our last scene, we will have an area that appears to be acceptably sharp, called our depth of field. In this scene, it is from this point to this point. In a hypothetical 8 by 10 print of this scene, viewed from about 25 centimeters away, this area would appear to be acceptably sharp. This is where the circle of confusion comes in. This point on the focus plane is perfectly in focus on the sensor. This point, represented by the yellow line, comes to focus behind the sensor. Because this point is reflected back to the lens as a cone, it gets projected on the sensor as a circle. A similar thing happens with the point in the scene represented by this blue line. It comes to focus in front of the sensor and is projected as a circle on the sensor. These are the circles in the circle of confusion. Another way to think about them is as blur spots. What it boils down to is this. The circle of confusion is the largest blur spot that is indistinguishable from the point that is perfectly in focus. We've just seen that the blur spot, or circles, come from distances in front of and behind the point of focus, and this means that those areas are considered to be acceptably sharp. The circle of confusion is the limit at which we start noticing things getting blurry. A better way to term the circle of confusion would be to call it the maximum circle of confusion, because anything smaller than the maximum will look as sharp as the point that is in focus. This is important because we will need to know the limit, or the maximum circle of confusion, in order to calculate depth of field. And because we have already discovered that depth of field changes based on enlargement, sensor size, and viewing distance, the maximum circle of confusion also changes. If we were shooting a photo that would be printed very large and viewed pretty close up, we'd want to use a smaller maximum circle of confusion, resulting in a larger depth of field. Now we have to take a step back and realize that you do not have to go into this super technical mode of thinking and run calculations every time you want to shoot. What talking about this will do is help you to understand how all of the pieces come together as we go through this course. With that said, how does all of this relate to aperture? I mean, that's really the point of this discussion, isn't it? When we stop down our lens, we are restricting the angle of light to a much narrower beam. The result is that it increases our depth of field, because the points that would be larger than the maximum circle of confusion at a larger aperture are now restricted and fall in the range of our maximum circle of confusion, and thus appear to be sharp. The light from those same points are entering the lens from those larger angles, but the aperture restricts them and alters our depth of field. Now that you have an understanding of how depth of field works, you're ready to move on to the next lesson: hyperfocal distance.